Okay, we are Team 7, and we're doing Crush 1. So this is our beta design for our Crusher. It's pretty much the same. Actually, if you go to the next slide. So this is just it inside the thing, but we have animations showing that our jaws are actually different. Instead of the teeth being aligned in a horizontal fashion, they're vertically. We did that because we wanted it to show that instead of rocks being trapped down in the base, we were finding that you'd get rocks down there, and then you get large stress concentrations. So if we align the teeth in a vertical manner, you have less of those concentrations because the rocks are able just to fall down smoother than getting trapped in that sharp edges. This is what our design is going to look like inside the actual frame. There's going to be panels on the sides and a panel on the top where the feed system is going to be incorporated so that the rocks aren't going to just be shooting out the sides. We just did this open concept so that you could see how everything would connect inside. We have our brackets here that our camshaft connects to, which our power team talked about earlier, and our sprocket, which connects to their power team. Our lever arms are actually going to connect up. In this model, they were just kind of floating down for some reason, but they're going to be connected to the base here so that it'll keep it all in line. We actually have an animation that shows. Let's see if it runs. So this is our animation. This actually has our vertical teeth in it, and we have brackets on the top and the bottom that actually lock the teeth into place, and then it goes into the ability to rotate these teeth out, so you can use the teeth 4 times in total before you actually need to buy new stock for the teeth, which is going to improve like the durability of the machine and the elongation of the actual process that you can use each tooth for. So instead of having to change out a plate every couple months, you only have to change out the teeth every like over a longer period of time, so that makes it more efficient.
Alright, so when we were doing the FEA for this, we trying to think how we're going to model a rock in the jaws, because the rock's not going to perfectly, fit all the area in the jaws. There's not going to be a lot of contact area. So for one side of the plate, we decided to model a 1 square centimeter contact patch with 5,000 newtons of applied force, which is about 50 MPa of pressure, which is enough to break white marble, limestone, and other metamorphic rocks, which is pretty much what we were shooting for. So, and then the material I chose to model it with is AISI 1020 steel, some low yield strength steel, just to see if that would work, because it's cheap, and if that's strong enough, then other steels will be strong enough. So, our peak stress was 85 MPa, with our yield stress being 351 MPa. So we had a factor of safety of about 4. Next slide. So yeah, here's our stress concentration in the fillet of our cammed shaft. Pretty much that's to be expected where the stress concentrations would be. Everything else is pretty geometrically normal and regular. Yeah.
Yes, so most of our stress concentrations end up being in the cam system on top. That can be a problem, because if that shaft actually bends, it'll misalign the jaw, and the jaw can become jammed up, and the machine will be completely destroyed. It turns out that the stresses on the pin joints on the bottom, you actually don't get a lot of stress because of the motion of the jaw is tangent there or whatnot, so it ends up being mostly concentrated at the top. Nearly all the stress concentrations end up being in here on this fillet of that little crank right there. And the strain here is magnified quite a bit. It's moving, just like a minuscule amount in this part. And our idea to prevent mechanical failure of the main rock crushing assembly, we're thinking that the chain should be properly sized so that fails first, or some pin joint should fail, so that there's never a situation where we can apply so much torque to the machine that will actually break it.
As shown on that graph, the 3 main objects that had the highest chance of a failure would be to change the camshaft or the lower supports. Questions?
So now you're using like vertical teeth.
Yeah.
So how do you mount those teeth?
All right, I can answer that. So let me go back a little bit. You might not be able to see it very well, but see these top little. Oh, you can't see the mouse. Never mind. These little guys right here are bolted into the plate, and pretty much what it is, it's a little pocket, a little square cross-section pocket. So you would unbolt this top part, take that off, slide the stock into these pockets, where there's square little pockets that fit in those pockets, which this is an identical version of that. Then you put that top over, so it has two pockets, if you will, kind of holding that in place, and then it sits up against the backrest of the plate. It makes it really easy to interchange them, because if they get worn out, take off two bolts, slide them out, slide new ones in. Super easy and quick.
And the plate's also going to have chamfered out grooves where the stock's going to fit in, so there's not going to be any, the stocks aren't going to be banging up against the backside of the plate. They're just going to be resting in there nicely.
Are the teeth actually vertical?
Yeah. Yeah, just kind of.
Are you worried about the rock just sitting in there?
No, it'll be depending on the angle of the jaw, as the jaw moves, and if the coefficient of friction between the rock and the jaw face is high enough, and that angle is fairly shallow, it'll actually jam the rock in there and then crush it so it can't pop out.
What if it's too low?
Yeah, like if it's so if the jaw's
Would
angle,
the rock just slide up and down if the coefficient of friction is high enough?
yeah, or if the angle between the jaws is too high, it'll do that too.
Okay.
But that's easily adjustable by basically changing the lengths of those lower arms and then moving the mounts on top. Yeah, so it's something we'll just have to adjust when we actually build it.
My other question is, how much torque is required just to move the jaw?
Just move it.
It's on a cam. So.
Yeah. We didn't like to free spin it. We didn't figure that out.
So, with the image with the frame, you said that the kind of the legs or whatever were floating in air. How were you going to attach it to the frame again, and how would you want to try and place the sifter underneath it? Like, how would that work as well?
Okay, so these are actually just going to be bolted onto the backside of the frame.
Oh, okay.
And then where we'd catch, or like where the sifter and catch cans would just be directly under where the jaw opening is, just so that the rocks can easily fall straight through and it wouldn't impede any of the motion of the jaws in any way. And this system is actually like, you can raise and lower this. The team that was in charge of that made it so that you could actually higher and lower it depending on the size you need. So there should be no problem with the clearance issue of those cans or the catch system.
Also, to build on that, because of cost constraints, we're going to have to shrink our design a little bit. So if this whole thing kind of was smaller and up here a little bit, there would be more room for the sifting system underneath it. And this is more of our final design. So those legs right here, that would, instead of kind of mounting to the ground in that fashion, that would then mount to the frame. So that's what we kind of have to fix.
I have one other question. Your jaws are super strong. Are you worried about those adjustable links bending and buckling?
The lower supports?
Yeah.
Yeah, not one of the simulations we did. We were applying 5,000 newtons.
Is that accurate?
No, sorry, 50 megapascals to a 1 centimeter by 1 centimeter square, which is enough to crush like a perfect rock with no fractures or anything like that in it. But there was forces on those legs, but it wasn't really enough to buckle them. So. But we also had we're using hollow tubes in that simulation also. We can just increase the thickness of the tubes or make them just solid bars. And for that cost, I think we figured out just the cost of materials to build it. It was over $600, and so we'd have to scale it down like a quarter of the size. So it'd have to be this big instead of this big to be cost effective to actually build. But we're worried that I was worried that if we do that, it won't be worthwhile to actually use it because you can only crushed rocks are like maybe this big at that point, and then you're probably just better off using a hammer.
Thank you.
Thank you.